I have many shirts.
I'll believe it when I see it.
I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for your creation and us being able to study it. And I just pray that you be with us today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so as you noticed a second ago, hopefully, we have this lovely Top Hat code. The enter join code is 941675, and 9860 gets you in here. So if you haven't done that already, do that. What matters more is that you sign this paper, or not even sign it, but just initial it. I will take paper attendance if you happen to be in the sports ball or something like that, and they ask me, how many times did Johnny miss class? I'll be like, I don't know. And I'll look at my piece of paper, and then I'll like roughly count from that, and I'll tell them that. I will not go to Top Hat and go, this many in Top Hat, because I sometimes forget to Top Hat. So the paper attendance is like more serious for me. I will Top Hat though, because I'm supposed to, so I'm sorry if that's confusing, but such is bureaucracy. Or maybe people who don't follow the rules. Maybe it's my fault. It's probably my fault. Let's see here. All right, so let's get going here. So I will begin with an example. Whoa. Example 1. So we have ring of radius A has uniform positive charge Q distributed around it. We're supposed to calculate the electric field at a point along the axis of the ring, a distance x from the center of the ring. So I'll draw a picture here. Here's my ring. Here's the center. Here's the axis. All right. And what we'd like to do is to calculate the electric field right there. And that's a distance x, like this, right? The radius of the ring is A. So there you go, that's A. All right. I'm going to fall someday, and it's going to be hilarious. That will for sure improve my course evaluations. I know it. I know it. I should probably just try to fall on purpose. Need to go watch a bunch of like old Chevy Chase and see how he did it. Let's see here. Sorry, that's no one you guys know who that is, and that's just as well. But anyway, so if we have this charge Q distributed around the ring, to find the electric field due to this charge at this point over here. So these are the source charges. This is the field point. We're trying to find the electric field at the field point. What we need to do is we need to think about the electric field from each little bit of charge, and I'll picture the one up here because it's easier. Like there's a little bit of charge up here, dq, right? And if you think about it, like that, it's going to make an electric field that goes like so, right? And it's going to be an infinitesimal electric field, like that, because it's an infinitesimal charge, right? Now, what happens with that charge? There's also what? It's got a partner in crime, right? There's another infinitesimal charge down here, right? There's the dq down here. What's it do? Same song and dance, right? But this way, right? And if you think about this, as we go around the ring, right, there is going to be a cone of electric fields that are created by the charges, right? Like, as you think about it, there'd be like a cone. The electric field goes this way, and then this way, 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 like that, all the way around. And every one of the vectors in that cone has an equal and opposite vector on the other side in one sense, like in the perpendicular sense, right? What's the only thing that adds together? Because as you can see, like, this part cancels, right? You can see from the symmetry here that the net electric field is what? This is going to be the direction of the electric field, right? The question is, what's the magnitude? So what we need to do is we need to add together the x components of each one of these. So I'm going to let you guys look at that for a second, and then I'm going to erase it because I need to draw something there. We good? I'm only going to erase the blue part. So what I want to do is figure out not the whole electric field, but just the x part, right? Let's say dEx. What's that equal to? So if you look at it, what we have is cosine theta times dE. Now the theta I'm talking about is right here, which is also over here, right? And let's see here. I can do a little bit better, right? Because I could draw that triangle down here, you know, just to isolate it from the picture for a second. I've got theta here. This is x, right? This is a, right? What's dE? Well, first of all, let's do cosine theta. What's cosine theta? Well, cosine theta is what? X over.
Just as wrong as it can go.
Wow.
Almost impressive.
Oh, okay. So x over, what's the hypotenuse here? Square root of x squared plus a squared, right? That's the hypotenuse. So the cosine theta is this. And how about dE? Well, dE is k dq, and then we have to divide by the squared distance between the source charge and the field point, right? What's that distance? This distance right here, right? That is the square root of x squared plus a squared, just like I said a second ago, right? So the Coulomb force, the magnitude is k times q divided by the distance between the source and the field point, which here is that, so I have to square it. So I've got an x squared plus a squared down here. Or if you like, I could write the square root squared. We good so far? So that's just the electric field due to that one infinitesimal charge, right? So I can, but I kind of want to express that a different way. So we want to think about this dq being distributed over, let's say, ds, infinitesimal arc length. So the situation here is this, that dq ds is equal to, well, the whole charge divided by the whole arc length, right? The uniformness of the charge distribution means that the charge per unit arc length should be the same as the total charge divided by the total arc length. Well, what's the total arc length of a circle? 2 pi r, but here r is a, right? So 2 pi a. So this gives me that dq is actually equal to q over 2 pi a ds, all right? So I could take that and I can put it in over here. What do I get? I get that dEx looks like kx over the square root of x squared plus a squared cubed. Put those all together, all right? And then my dq is q over 2 pi a ds. Now I probably could have done this problem without the ds thing, but I think it's not bad to do it this way. All right, so then what? How do we find the total electric field? We do what? We have to add them up. How do we do that? We integrate, right? So the net electric field at this point is going to be the integral over the ring of kx q ds divided by 2 pi a square root of x squared plus a squared cubed. The good news is you guys have all passed Calculus 2 and you're experts at integration. Right?
Yeah.
And none of that matters because the integrand here is constant over the ring. See, k x q 2 pi a square root of x squared. Don't worry, we will integrate today.
Sweet.
I won't make you feel like your Calculus 2 was in vain altogether. It was not. It matters. But you see, everything there is independent of the point on the ring, except for ds, of course. I mean, we do have to integrate that. But what is the integral of ds over the ring? S? Well, yeah, I mean, in some sense, but the total S, right? So this is 2 pi a, right? Because that's the circumference. So that 2 pi a cancels this 2 pi a, right? And we're left with, answer, the electric field, the magnitude at least, is equal to kx q divided by x squared plus a squared. I guess I could say to the 3 halves, right? And there you go. Hooray. It's kind of funny. I think actually this example, in some sense, is easier than the line segment one we did the other day. In the integration sense, it's easier, but there's more geometry to think through here, right? Yeah.
Sorry, what's the business with the 2 pi a coming and canceling with the denominator?
Well, the integral over ds is the net arc length, but that's 2 pi a. So the other way this could have been done, Kirk, is if I had not introduced this whole thing, if I just said, well, like here's another way to do this calculation, you could have been like, well, E is equal to the integral over the ring of k dq, k dq over, you know, x squared plus a squared to the 3 halves, right? And I could have just been, and there's an x. And I could have just been like, well, that's xk over x squared plus a squared to the 3 halves, integral over dq over the ring, right? Like that's another legitimate way to do this calculation. But it's a more physicsy calculation. But this is a physics class, so I could also do that by rights. So could you, if you understood what you're doing. What is the integral of dq over the ring? It's the total charge on the ring, which is given to us to be q. So we find the same answer. But I was reinterpreting the integral as an integral over arc length because that's more familiar to you from your calculus sequence. You've done integrals over arc length, right? That's a known calculation. Integrals of dq over a ring, that's kind of weird and new. But it should be actually, how do you define the integral over dq? It is defined by exactly what I did here. You have to reinterpret it as an integral over arc length subject to this relation, like dq ds is equal to the charge per unit length, which in this case happens to be constant. Anyway, there you go. That is the electric field at this point due to ring of charge. Now what's the question we always ask in here? Like the asymptotic question. What happens if what? What would happen if x was way, way bigger than a? What happens then? If x is much, much bigger than a, what would happen here? It approaches Coulomb's law, right? Because essentially then x squared plus a squared is to, you know, for all intents and purposes, just x squared. And so then you have x over x cubed, which is 1 over x squared. So you get kq over x squared, which is Coulomb's law for a single point charge here. So if you're very, very far away from the ring, you lose, you know, the geometric dependence on the size of the ring in the electric field, right? On the other hand, if x is very small, it's pretty far. It's more noticeably different than Coulomb's law, right? For example, if you put x equal to 0, the electric field's what? And does that make sense? What happens at 0?
It's
What's this formula do? Put x equal to 0 and what happens?
It goes to 0.
It goes to 0. Does that make sense? Why should the electric field be 0 here?
Because of that equilibrium in the center of the...
Is that equilibrium?
Oh, we agree. Good. I was going to say, but that's right. But it's because the electric field from all the infinitesimal charges distributed around the ring, they all have equal and opposite fields which just cancel out. But like you said, it's an equilibrium is another good way to look at it from like a force perspective. Okay, well that was fun. Next. How about a disk? Uniformly distributed charge. All right, and I'll try to keep the setup kind of similar looking. So I'll draw the disk like this, all right? And I'm asking what's the electric field over here at a point here, let's say a distance, well, x. And let me see, I'm trying to follow your textbook. This is actually example, I know you're like, follow the textbook, what? Is this a dream? What's happening? No, okay, so example 21.11 is pretty good, so let's do it. So they give the radius, the big radius of the ring to be r. So I'll draw like here. So we have a ring of radius r. All right. So just to recap, this is example 21.11 in your text, which I think is worth covering. Sadly, it's not in my notes. So, you know, my notes are a work in progress, and sometimes they're better than the text, sometimes they're not, and a lot of times they're not. Surely the text has better grammar. That much is certain, right? So if this is a uniformly distributed charge, so I'm saying the charge is on the whole disk. So usually for a surface charge, we talk about sigma, which is dq, and we could say dA. It's the charge per unit area, right? So for this disk, we're talking about q over, what's the total area for a disk? Pi r squared, right? So dq in our current situation is going to be like q over pi r squared times dA, right? Although then that begs the question, which dq are we thinking about? So what do you guys think? We could jump into the future like three quarters of the way through the semester in your Calc 3 class where you've actually defined double integrals. Yeah? But let's not do that. We can do other things. No, what we should do is we should scaffold our understanding off what we've already done. We did it example 1, right? So what we can do is make example 1 work for us. What we'll do is take the disk and divide it into a bunch of circles. So we'll just look at like a ring, right? Like a ring at radius r. So if you want me to draw the disk dead on, it would look something more like this, right? Here's the ring, and then here's the center. So we're talking about this at r. So we're talking about the infinitesimal charge around this that goes from r, and the thickness is dr, right? So in view of that, if I look at it that way, what's the area what's the area I'm about to shade? What would this be? Because that should be the dA I put up here. So we got ourselves a q over pi r squared. The dA is 2 pi little r dr. The circumference times the thickness. If you took this little band and you laid it out flat, its height would be dr, and its length, or its width would be dr, and its length would be the circumference of the circle, which is 2 pi r. Little r is a variable. Big R is a fixed constant here. So there's my formula for dq in terms of where the ring is. right? And so forth. So dE will be k dq divided by the distance, which in this case is what? The distance, so this is what makes this work, of course, is that everything on the blue ring, it's all a distance of the square root of x squared plus little r squared away, right? So dE would be k dq over x squared plus r squared. But what happens? Same story as the last one, right? The net electric field is going to be straight over. We know that we're really just looking for we want the x component. So, to get the x component, we multiply by cosine of theta, which here is what? Just like the last example. The cosine of theta, just trying to pick out this piece here. That's the part that doesn't cancel. So we got x over what? Square root. Anyway, we didn't need to go through all this again. Like, we could have just got straight to the point of, and I really can say dE here. I'm sorry. I do have to have dEx when I go to the integration. After I do the integration, all the y components or z components, whatever you're going to use for their labels, those cancel out. But at this stage in the game, I shouldn't really do that. Anyway, the point here is that is kx dq divided by x squared plus r squared to the 3/2. Now, all right. Now let's put it all together. So to find the electric field, we know from symmetry it's just in the x direction. And so we're up against the following calculation. We need to integrate k, x. Now my dq is actually big Q times, I guess I could simplify this a little bit, right? The pi's, they be canceling, right? So we just got ourselves a what? A Q times 2 r dr divided by, what we got here? Big R squared, and we still got this x squared plus r squared to the 3/2 power, right? This is an integration over the radius of the little ring. What is that range over? Every time you set up an integral, you should ask the question, what's the appropriate range for the integral? Right? The physical setup determines that. Here, our little r ranges from 0 up to what? Big R. So this integral should go from 0 to big R. Unfortunately, I mean, I can pull some stuff out of this, right? We've got k is a constant, 2 is a constant, q is a constant, x is a constant, big R squared, that's a constant. And I think that's about all we get. So the integral from 0 to r, what you got here? You got r dr divided by x squared plus r squared to the 3/2. Now, I need to consult my resident Calculus 2 experts. How do you do this integral? You're like, I already passed Calculus 2. I don't have to know it anymore, right? Yeah? Did I make a mistake? Is there a mistake? What's that?
Why you factored out the 1x in the numerator and not the 1 in the denominator?
Oh, because I can't factor out the x in the denominator because it's paired with the r squared in the 3/2 power. Yeah.
Did you use U substitution for the R?
U substitution for the r. Yeah?
Why is the small r trapped inside of the integral and not the big R?
Big R is a fixed but arbitrary constant which describes the size of the disk. Little r is a variable that describes the size of the ring that we're integrating the charge over. So they're different. Big R is a constant, little r is a variable. I think U substitution might work. Yeah. It's just that, isn't it? We let U equal to x squared plus r squared. X is a constant here. So du is what? 2r dr. I should have left the 2 inside. I'm putting it back in. Putting it back in. There we go.
Welcome back.
Now, u of 0 would be equal to x squared plus 0 squared, which is just x squared. And u of r would be equal to x squared plus big R squared. And you're like, what are you doing? I'm changing the bounds, something that you guys fight me kicking and screaming to learn in calculus 2. I don't know why. So we are integrating from x squared to x squared plus r squared. I should be careful. I usually make an error when I say something prideful like that. As you know, pride goeth before the fall. Du is 2r dr. And downstairs we got ourselves a what? U to the 3 halves. This we can integrate, and we get what? kqx over r squared. And the integral of the 3 halves power is what? We add, that's a minus 3 halves actually, right? So minus 3 halves plus 1 is, minus 3 halves plus 1 is minus a half, minus 1/2. So we actually get a minus the square root of u, I believe, evaluated from x squared to, now you gotta check me on that.
Shouldn't it be 1 over the square root of u?
Yeah, 1 over the square root of u. I was like, that's not right. Thank you. Oh man, look at that. See, this is what happened when they clean the board with water. Actually, it's not even a board. It's I got that from Home Depot for 20 bucks, truth be told. But it was up in the physics room, but I stole it for us. It's my board. So I'm allowed. And not having something to write between these 2 boards and like walking back and forth, I would go insane. Let's see here, more than usual. 1 over square root of u is what you guys told me, right? Do I owe you a 2 there? Is there a 2? If I differentiate that, I get a minus 1/2. I feel like there's supposed to be a 2 up here, right? Because the integration rule, we have to divide by n. But here n is minus 1/2, so 1 over minus 1/2 is minus 2. Anyway, differentiate this with respect to u, and you get that. Okay? So then we plug it in, we get kq x over r squared, I'll leave that out front, times, and I'll put the 2 out here. Like, make up your mind where you can put the 2. And I'm going to do 1 over the square root of x squared minus 1 over the square root of x squared plus r squared. I absorb the minus by flipping the bounds. Es bueno? Well, we can clean this up a bit, yeah? Yeah.
Couldn't we just take the formula we got for the ring the first time, integrate all that?
That's what we did.
Sorry.
That's what we did. Wait, what did you say, Otto? So if you're saying we should do what we did, I'm on board with that, for sure. So I'll definitely buy that. Let me put it over here. So, well, we don't really need this picture, do we? I'm taking back this space. It's going to be a safe space for our formula. Let's see here. Don't ever say I don't believe in safe spaces. Let's see here. So my electric field formula is, oh, and so this x is positive too, right, by assumption here? So x is positive. So this is just 1 over x. You know the square root of x squared, what is it generally? It's absolute value of x. Because that's the definition of absolute value of x, actually. Anyway, so that x cancels the other x, and what you got here is a 2kq over r squared, parentheses 1, and then minus x over the square root of x squared plus r squared. Now, I messed up. I was supposed to write this in terms of sigma, actually. That's the custom. So what if we want to express this formula in terms of sigma instead? Can you guys help me out with that? How would we do that? Sigma is what? Sigma is equal to q over pi r squared, right? I've got a q and I've got an r squared. So I feel like that 2 is wrong. Yeah, the book's got a half.
Would it be because the?
Did you guys tell me a half at some point?
I think because when you find the derivative, it puts a 1/2.
Oh, yeah. I'm an idiot. So that's supposed to be a half, guys. Let's think through this. The derivative with respect to u of u to the minus 1/2 is what?
-2 to u to the -3/2.
So it's minus 1/2 u to the minus 3/2, right?
Yeah.
Something not right here.
Wouldn't that make the 2 right where it was?
Yeah. Sorry, guys. I'm something not right here. Just a second, guys. Oh. It's fine. Let's keep the 2 where it was. Let's trust the math. Trust the process. Don't see my bad. I'm trying to correct to the book's formula, and I'm ignoring the fact that the book does not have k. The book has a sigma and an epsilon naught. There's no k in the book's formula, so I'm trying to match up with something which is not what's in the book. All right, so great. Look, we want to bring the x inside here. How do we do that? Well, let us make the sigma correction. All right, so we've got q over r squared is what? It's pi sigma, right? So we've got 2 pi sigma times k, right? Fine, there's that. 2 pi sigma k is how to rewrite the front thing in terms of sigma rather than q and r squared. Now the other one, yep.
Where do you say K is represented by in the textbook?
K is, for everybody, 1 over 4 pi epsilon naught. Like, this is,
So they just write.
that is like the convention of physics.
And you said they don't have the constant K in the textbook.
No, they do.
Oh, they do.
This is not just this textbook. Every textbook does this.
So what were you saying was not in the textbook?
What I'm saying is that the way I've derived the formula, I have k in the formula right now. I'm going to put it in terms of epsilon naught eventually.
Oh.
And when I do that, it's going to take this 2 up here, and it's going to divide by a 4, which gave me a half in the formula. Just let me get to it. Yeah.
Would the pi be, would it be sigma divided by pi?
No. Well, I mean, take this right here, and you can solve for q over r squared equal to pi sigma, right? That's all I did. I traded a q over r squared for a pi sigma.
Gotcha, sorry.
All right. Let us factor the x inside. So if I bring the x down here, how's that go? What happens when you bring x down? First of all, x in the numerator is actually what? 1 over 1 over x, right? Everybody agrees? And what does it get me if I bring it inside the square root? When I bring the 1 over x inside the square root, it becomes 1 over x squared. So what I get is I get 1 plus r squared over x squared is what happens there. All right? And finally, let me finish and make it match the book's answer here. So what we've got is a sigma over 2 epsilon naught times 1 minus 1 over the square root of 1 plus r squared over x squared. This is a really nice way to write the formula for the electric field here due to a disk. At a point on the axis of the disk, a distance x away from the surface. Now we should again think about the asymptotic case, right? What happens here? What would the asymptotic case be like? How about when x is much, much greater than r, what happens? Electric field is what? Yeah, this piece drops to what? Well, if x is much, much greater than r, then, wait a minute, x much, much greater than r? Oh yeah, it just looks like 0, doesn't it? Huh. Oh, well, I mean, that's true, but there's a better approximation. Well, I probably need like the binomial series here to see it. I do think that's the formula the book has too. R squared over x squared, yeah, plus 1. Well, the book claims that this quantity is much less than 1 in this situation. No, I don't believe that. I think I'm just, you know what, I think there's a simple explanation here, guys. Oh. This is true, it's 0, okay? Yeah, you guys are right. Let math do its work. But let's think about a more interesting case. If x is much, much less than r, on the other hand, then the electric field is approximately what? Yeah.
Would it not be sigma over 2 epsilon?
That is exactly right. It is sigma over 2 epsilon naught. And why is that interesting? Think about these two limits. If we think about the size of the disk, right, being very, 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 very large, right, and you're just a little distance above the disk, that's this limit. So an application of this example is the following. If we have a ginormous plane of charge with charge density sigma, right, then if you go a distance x above the plane, then the electric field points upward, and the magnitude is simply sigma over 2 epsilon naught. Because we can approximate a plane by an infinitely large disk. So in a limiting case, this example gives us that the electric field of a planar charge is sigma over 2 epsilon naught. And that's independent of how far you are from the plane. subject to the condition that the plane still is big relative to that distance. Right? We talk about infinite planes in here. Of course, is any plane infinite? Not really. This is an approximation, right? So like this desk in front of you guys is infinite if we're talking about something like that kind of height, right? Even that's still not quite legitimate, right? Like it's even less legitimate if we're talking about the height of a marker, right? It's even less legitimate if we're talking about the height of two markers, you know, and so forth. But these are good approximations. So once you know this, well then you can take this example and build new examples. Like, what if you've got one plane here with charge sigma, and you've got another plane down here with charge minus sigma, and then I ask, what's the electric field here? What's the electric field here? What's the electric field here? We'll start with the middle. So let's call this sigma 1 equals to sigma, and sigma 2 equals to minus sigma, just for the sake of discussion. So if it's minus sigma, that means that you've got like this, you know, minus. Well, I'm gonna put the direction. So we got sigma over 2 epsilon naught. It points down, right? You could call that E2, and then the E1 from that one. Oh, it's also this way, right? So E1 is also sigma over 2 epsilon naught. So in short, the electric field here, sorry my picture is getting so messy. The electric field there is equal to the sum of these two. So it's sigma over epsilon naught, and I'll just say downward. I could throw some vector in here to make you guys less comfortable if you'd like. What am I talking about? You guys love vectors. You had Physics 231. You know vectors. Vectors are your friends. Vector fields, you'll soon appreciate those more. So down here, again, so down here, the negative charge, it sucks. This is E2, right? And this is, down here, this is E1. And the magnitude's always sigma over 2 epsilon naught. I'm just putting the directions in with the arrows, okay? So the electric field down here would be what? 0, right? And a similar argument shows that the electric field above the other charge is 0. Only between the two charged planes do we have a non-zero electric field. Does this example matter to any of you? Why? What if I made it look like this instead? Yeah, this is a capacitor. That's the electric field between a capacitor with large plates. That's how it works. So this is not just an exercise for me to share my love of vector calculus with you, although it is that. I enjoy different things about this course than you guys do. That's okay. But hey guys, that's it for today. So have a good weekend. We do have a problem session in DeMoss Hall, 4424, starting when?
6 o'clock.
No, it ends at 6 o'clock. But it starts at like after my next class. 4:15, I think. Yeah.